Okay, it's Brian. We're talking about the review and practice from day 5. This is material that spans the whole course. The final exam is going to be comprehensive, and we're going to be talking about basically things in the world that we can explain using the physics that we've learned this semester. Okay, and so when I was working on the final exam, I was looking for things in the world which we could use physics to explain, and I wrote a couple of exam scenarios for it that will appear on your actual exam, and then I had some ones left over, and some of those are some of the problems that we'll see in this particular set, as well as some from previous exams. So these are exactly the kinds of things you're going to be seeing on the final. So this is really, really good practice, and in each case, the crucial thing is they're going to look at what's happening, think about the physics of what's going on, and think about how we can use the physics to illuminate what is happening. So our first scenario is the porpoising penguins, and it turns out penguins sometimes leap out of the water, and they do these little parabolic trajectories through the air. And there's a couple of suggestions as to why they might do that. They're treated in the exam scenario. But fundamentally what we're doing is we're analyzing one of the leaps that a porpoise does. And they leap from the water at 2.8 meters per second at a 32-degree angle. And we want to analyze that leap. And I'm going to do the problem first. There's no rule that says I have to answer the questions first. So I'm going to go ahead and take a look at the problem. And for the data given in the problem statement right here, the question is this. 1, how long will the penguin be in the air? What is the greatest height above the surface that the penguin reaches? And then how far will the penguin move horizontally before splashing down? Well, of course, the physics that we're looking at here is the physics of projectile motion. So a penguin leaves the surface of the water, traveling at a certain speed v. And remember how we treat such problems. We break the motion into two components. We break it into a Vy, and we break it into a Vx. Okay, now the penguin leaves the water at an angle theta, and we can say that the x component, Vx, is equal to V times the cosine of theta. Vy, the y component, is equal to V times the sine of theta. For the data given here, where the speed is 2.8 meters per second, we come up with values. The x component of the velocity, and I'm going to keep one extra significant figure because we're going to be using these in further calculations. So we're in an intermediate stage of the calculation. We'll keep one more piece of one more significant figure. The x component is 2.37 meters per second. The y component is 1.48 meters per second. Now remember how we solve problems like this, okay? The vertical motion, okay, is just up and down, and it's free fall. Okay, and the vertical motion determines how long the penguin is in the air, because once it comes back down to the water surface, it's game over. While the vertical motion is happening, while we have that free fall motion happening, the horizontal motion is just uniform motion at a given speed. So the first piece we want to do is we want to take a look at the vertical motion, and the penguin leaves the water at a speed of 1.48 meters per second, moving upward. That's going to determine the time the penguin is in the air, and then subsequently we'll come back and say while it's in the air, it's moving horizontally at this speed. So we'll come back and use that to compute the horizontal distance. But for the vertical motion, the penguin starts by moving upward at positive 1.48 meters per second. It finishes moving downward at 1.48 meters per second, so a velocity of negative 1.48 meters per second. The change in velocity between the initial and the final is negative 2.96 meters per second. And with that in hand, we can calculate the velocity, because remember, this is free fall. For all accelerated motion, the acceleration is equal to the change in velocity divided by the time interval. Well, since this free fall, the acceleration is negative 9.8 meters per second squared. The change in velocity is negative 2.96 meters per second. I can calculate a time interval. If I do that, I get a time interval of 0.306 seconds. And with that in hand, I'm just going to come back here and calculate how far the penguin moves, because during that 0.3 seconds, it's traveling horizontally at 2.37 meters per second. So the horizontal distance it's just going to cover is just equal to Vx times the time interval, 2.37 meters per second, times my time interval of 0.3 seconds. And so I get a horizontal displacement of 0.71 meters. Okay, so my time interval, 0.3 seconds. My horizontal distance, 0.71 meters. Then the third piece that was asked, and it was actually part B, but there's no rule that I have to do part B before I do part C, is what is the greatest height above the surface of the water that the penguin reaches? Well, remember, it leaves the water at 1.48 meters per second, okay? And we know how to calculate how the height that something will reach if it leaves the ground at a certain speed. We did a whole bunch of problems like that back in chapter 2. And I'm going to use this equation. Vf squared is equal to Vi squared plus 2 times A times delta Y. Delta Y is going to be the height that the penguin reaches above the water. For this problem, the initial speed is 1.48 meters per second. The final speed, when it reaches its highest point, is 0 meters per second. And the acceleration, of course, is just the acceleration of free fall. That's negative 9.8 meters per second squared. With everything in hand, I can calculate what delta y is. If I do that, I get a change in height of 0.11 meters. And so that's my third piece of the problem. So how long will the penguin be in the air? 0.30 seconds. How high will it go? 0.11 meters. How far will it go? 0.71 meters. And here's a quick assessment. We were told in the problem that the penguin has just enough time to catch a breath. Now, it takes the penguin a quarter of a second to catch a breath. The time that we have here is 0.30 seconds, just a little bit more than a quarter of a second. And so everything seems good. Now, let's come back and take a look at question 2. And question 2 asks, if the penguin wants to get the maximum amount of time in the air, well, for the maximum amount of time in the air, I want to have the biggest possible vertical velocity. The vertical velocity is v times the sine of theta. If I take theta and make it 90 degrees, the sine of theta is equal to 1. The vertical velocity is equal to v. That is as big as it can possibly be. That is going to give me the most possible time in the air. And so the answer to this one is 90 degrees. Now, when I talk to people about it, the most popular choice was 45 degrees. 45 degrees is what gives you the maximum possible range. But the problem didn't ask about the maximum possible range. It asked about the maximum possible time in the air. And for that, you want 90 degrees. That gives you the most hang time. And now to question 1. Because one of the things that was mentioned in the passage was maybe penguins do leaps like this so that they can just experience less drag force. Now remember, our expression for the drag force is this. Drag force is equal to 1/2 times the drag coefficient times the density times the area times v squared. V is the speed that something is moving at, okay? The drag coefficient has to do with the shape of an object. The area is just how big is the object. The only thing which is different between water and air is the density. And water is about 1,000 times as dense as air. And so as a consequence, you're going to experience a drag force that's about 1,000 times as big. And it's related to the density. The drag force basically comes from the fact that when you're moving through a medium, you have to push it aside to make room for yourself. And if the mass is greater, it just is more expensive to do that. So the answer to that one is, in fact, C. Let's take a look at the next problem. And this one has to do with lions chasing zebras. And there's great data for lions chasing zebras. And we have some data for lions chasing zebras given here. We're given accelerations, we're given top speeds, we're given circular accelerations, everything that we need. Okay? Now let's take a look at the questions first. Question 1, which animal reaches top speed in a shorter time? Well, we're told lions accelerate at 5.5 meters per second squared. Zebras accelerate at 4.4 meters per second squared. Lions reach a top speed of 14 meters per second. Zebras reach a top speed of 11 meters per second. Again, for motion in a straight line, the acceleration is equal to delta v over delta t. The time interval is just therefore equal to delta v, the change in velocity, divided by the acceleration. And if I crunch the numbers, what I get is that the time is less for the lion. The lion gets to its top speed faster. And actually, that makes sense. Predators are typically about the burst of speed that allows them to catch their prey. Next question, I want to think about, as the lion is getting up to speed, what can we say about its power? Well, remember, power is equal to the change in energy divided by time. And the energy that's changing for the lion is its kinetic energy. Now, the velocity of the lion is increasing linearly because we're told there's a relatively constant 5.5 meters per second squared. So as a consequence, the kinetic energy is going to increase this way. Now remember, the kinetic energy is equal to 1/2 mv squared. So the kinetic energy is going to increase with a parabolic shape like this because it's proportional to v squared. And if v is increasing linearly, the kinetic energy will increase with this parabola right here. And the power is basically the slope of the energy graph, okay? Because it's just equal to delta E over delta T. That's basically the slope of the graph. And so that looks like the slope is getting steeper as I get further out the graph, and that makes sense. Down here, the energy is not changing quickly. Out here, it's changing more quickly. So as a consequence, the power is increasing. Next piece, we look for the problem, we look at turning. And definitely in chases, there's lots of turns. And if an animal is turning in a circle, the circle has a certain radius. And typically that's true when you execute a turn. You're basically going in an arc of a circle. The acceleration is equal to v squared divided by r. And the question is, which is capable of a tighter turn, a lion or a zebra? By a tighter turn, I mean who has the smallest value of r. If I take this relationship and I solve it for r, it says the radius of the turn is equal to v squared divided by a. Well, v is their cruising speed, and lions are cruising at 14 meters per second. Zebras are cruising at 11 meters per second. And then when they're going in circular arcs, okay, lions have an acceleration of 6.5 meters per second squared. Zebras have an acceleration of 5.5 meters per second squared. If we work out for those numbers, what is the radius of the turn? For a lion, I get a 30-meter turn. For a zebra, I get a 22-meter turn. And that is typically true. The prey animals tend to be able to corner better, even though the predators tend to be able to accelerate in a linear sense more quickly. And so we get numbers like this. Who turns the tighter turn? The zebra. That's how we take a look at this problem. Next up, we've got one with dragonflies. And dragonflies are kind of interesting because for most things, they can corner at higher accelerations than they can speed up at. But for dragonflies, that's not true. Dragonflies can only achieve 0.5 Gs when they're doing a turn at a speed of 1.5 meters per second. But they can have a forward acceleration when they're speeding up from rest of 2.2 Gs, and they can do a vertical acceleration if you drop one and it has to like pull out of a fall. It can do a vertical acceleration of 4.2 Gs. Okay, so let's take a look at the questions first. Question 1. If a dragonfly has a period of constant acceleration at the noted value, how long would it take to reach a cruising speed of 1.5 meters per second? The change in velocity is equal to the acceleration times the time interval. The time interval is equal to the change in velocity divided by the acceleration, something we've seen previously. The acceleration that the dragonfly is given is 2.2 g. That's 2.2 times 9.8 meters per second squared. Remember, 1 g is 9.8 meters per second squared. And if we do that, we come out with a time that is approximately 0.07 seconds. For question 2, it asks if the dragonfly were able to fly in a circle with the noted acceleration, what would be the diameter of the circle? Well, the radius of the circle the dragonfly would go in, okay, at a speed v, and we're told v, the cruising speed, is 1.5 meters per second. The acceleration is 0.5 Gs, so 0.5 times 9.8 meters per second squared. That's my acceleration. and the acceleration is equal to v squared divided by r. Okay? If I calculate the radius of the circle, it's 45 centimeters, and so the diameter of the circle is double that, or 90 centimeters. Okay? Next piece asks for this. During the period of high acceleration during a drop, by what factor does the dragonfly's apparent weight exceed its actual weight? So what's happening is the dragonfly is moving downward at a slower and slower speed, and then it reverses course and moves upward. During that time, there is an upward acceleration, and the acceleration, we're told, is 4.2 g, and I'm just going to leave it as 4.2 g. Okay? The forces on the dragonfly are this. One is the weight, which acts downward. The other is the lift force, which is acting upward. It's flapping its wings. So lift, and I have weight. The net force is just equal to the lift force minus the weight force. But the F net is also equal to m times a. Okay? So here's my expression. M times a is equal to the lift force minus the weight force. But the weight force is just equal to m times g. And the acceleration is 4.2 g. So it's m times 4.2 g is equal to L minus m times g. And we're asked about the apparent weight. Well, the apparent weight is the contact forces that support something. And in this case, the contact force is just the weight. It's the contact with the air. So the apparent weight is equal to the lift force. And given my expression right here, the lift force is equal to m times 4.2 g plus m times g, or m times g times 5.2. And the question asked us, what is the ratio of the apparent weight to the actual weight? Well, the apparent weight is m times g times 5.2. The actual weight is m times g, and so I end up with the ratio is just 5.2. And this is one of those problems where I don't need to know the mass. The mass cancels, and actually I don't need to use the value of g. Actually, that kind of cancels too. And so by keeping it symbolic, I can save myself some work. Next, we're looking at walking the walk. Okay, and remember this, when back in chapter 6, when we talked about people walking, we said, look, when you walk, your body is pivoting over your planted foot. So as a consequence, your body is going in the arc of a circle. So the acceleration is directed towards the center of the circle. The net force is directed downward. The forces acting on you are the weight force and the normal force, which is acting upward. And since the net force is downward, the weight force is bigger than the normal force. The normal force is less than the weight force. And the smallest the normal force could be 0. If you were walking as fast as you possibly could, your free body diagram looks like this. At the midpoint of your stride, the only force is the weight. There's no normal force. You're basically at the hairy edge of becoming airborne. And so the acceleration is just equal to g, but the acceleration is also equal to v squared divided by r. So the speed that you're walking at is equal to the square root of r times g. And if we solve for what that is approximately a speed of about 3 meters per second. And if you don't remember this whole analysis, take a look at that. We did that back in chapter 6. We talked at walking speed, and it was basically a circular motion problem. Now the next piece of the puzzle talks about forces, okay? And we're thinking about the force on your forward foot, and we've talked about this previously. Question is this: when you walk on icy surfaces, you take shorter strides. Why is that? Okay, so let's take a look at the force on your forward foot. And we've talked about previously, there's a force parallel to the surface, we call the friction force. There's a component perpendicular to the surface, we call the normal force. The sum of those two forces is the ground force, which points along your leg. Okay, that has to be true. So if you swing your leg forward to an angle theta, okay, so the leg is swung forward like so, to an angle theta, the force goes directly along the leg. Okay, actually I'm going to draw that vector a little bit bigger. The force goes directly along the leg. There are two components. One is the normal force, which is the vertical component. The other is the friction force, which is the horizontal component. And the angle theta is this angle right here. Now I'm just going to call this F. That's the ground force. Okay? We want it to be like that. Now, let's take a look at the triangle. Basically, I've said if I take my normal force and I take my friction force, and I can take it and translate it so it's like that. And I have the net force, the ground force points like so. I have my angle theta here. The tangent of theta is equal to the friction force divided by the normal force. Okay? Oh, but we also know the static friction force, the biggest it can possibly be, is equal to mu s times n. So if we're looking at the biggest the angle can be, that means we want the static friction force as big as it can be. The biggest it can be is mu s times n. So get mu s times n divided by n. Tangent of theta is just equal to mu s. Oh, so theta is equal to the inverse tangent of mu s. Net result, what I get is this. If you're walking on normal pavement with a coefficient of friction of 0.8, the maximum angle is going to be 39 degrees. Now that's swinging your leg out pretty far. So basically, you can swing your leg out pretty far on regular pavement and you will not slip. But if it's icy pavement with a static coefficient of friction of 0.2, the angle is only 11 degrees, and an 11-degree angle is a pretty small swing. You aren't swinging your leg out very far at all. And the reason is because if you swing it out too far, the friction force gets bigger, and there's a maximum value that the friction force can have. So you walk with shorter strides on icy pavements, and the reason is, of course, a physics reason. And that is the fourth problem on this particular problem set. We'll be back with another one on Friday.